Hello, AP Chem students. So this video, we will be looking at the effect of temperature on spontaneity. All right, so in our last video, when we were talking about the situation with the water, where sometimes it will melt based on the temperature and sometimes it will freeze based on the temperature, these slides should give us a little more clarity as to how temperature impacts spontaneity. So where we left off in our last slide, we were talking about the second law of thermodynamics. All right, so if we have a spontaneous process, the entropy of the universe, delta S universe, is equal to the delta S of the system plus the delta S of the surrounding. All right, now thinking about delta S for the system should be not that bad because we're thinking about, the volume of the system, the state of matter, is it changing from a liquid to a gas, something like that. So it's the surroundings that are a little more difficult. So the effect of temperature on spontaneity. So let's just think about this reaction. We have H2O liquid forming H2O gas. All right, so a liquid vaporizing and becoming a gas. So if we think about the change in entropy for that system, all right, we're going from the liquid to the gas, the volume's increasing, we are getting a positive delta S. But what about the surroundings, all right? So water is the system, everything else is the surroundings. So how is this happening? So we gotta consider what's happening to the surroundings when that liquid becomes a gas. So let's just keep something in mind. When we think about endothermic and exothermic situations, all right? In an endothermic situation, energy is coming from the surroundings and going into the system. And in an exothermic situation, energy is coming from the system and going out into the surroundings. All right, so think about our water going from the liquid phase to the gas phase. All right. So something that we want to think about, entropy increases with temperature. All right, so as we move along those different phases, so now we kind of have like a sideways heating curve. All right, but as we increase temperature, entropy is going to increase. All right, as particles move faster, they are going to be able to get into more disorder. So an increase in that kinetic energy of the particles will mean an increase in entropy. So our average kinetic energy, of course, is our average temperature. So we have this graph over here, and we could see that T2 is a higher temperature because more of the particles have a higher kinetic energy. All right. Oddly enough, this graph kind of looks like all of those flattened curves you may be seeing. All right, but it's just a normal distribution. And if we are at a lower temperature, all right, we're going to have more particles closer to that temperature. So we want that higher temperature to have more entropy. So as we move up, as we move from liquid to gas, we're going to get this big increase in entropy. But for the surroundings, if we have an exothermic reaction, all right, if we have an exothermic reaction, the energy or the heat, it's moving out to the surroundings. The surroundings will get warmer, so there will be an increase in entropy. If we have an endothermic reaction, energy is being taken away from the surroundings, and we will have a decrease in entropy, right? Cooler substances will have less entropy. So if we remove energy from the surroundings, we're going to have less entropy. All right, so temperature and spontaneity. Entropy changes in the surroundings are primarily determined by heat flow. So anytime we're thinking about surroundings, we're thinking about heat flow. When we think about the system, we often want to think about its volume. All right, but for the surroundings, it will be basically our heat flow. We will assume a constant pressure throughout most of these questions. Exothermic reactions in a system at constant temperature increase the entropy of the surroundings. All right, so if we have an exothermic reaction, the surroundings will have a positive delta S. Endothermic reactions in a system at constant temperature decrease the entropy of the surroundings, so the delta S for the surroundings will be negative. Now, the impact of the transfer of a given quantity of energy as heat to or from the surroundings will be greater at lower temperatures. All right, so this is kind of an interesting point, that last bullet. What it is saying is that temperature will have an effect on the magnitude of the change on the surroundings. So let's just think about an example. Let's say I have $50 and I give it to a random person. All right, the $50 goes from me to that person. We could think of that as the heat flow from a hot source to a cold source. All right, that heat flow. But what if that person already has a lot of money? Does getting $50 really mean all that much to them? All right, probably not. Now, what if I give that $50 to someone that doesn't have any money? That's going to be pretty substantial. All right, if I give them that $50, they're going to be able to buy a whole bunch of stuff that they couldn't have afforded before, whereas the person who already had a lot of money, all right, it didn't mean much to. So giving energy to a system at a low temperature is going to have a more dramatic impact than giving energy to a system at a higher temperature. So now it's all going to come together in this one equation. All right, so for today, we want to think about how can we calculate the delta S of the surroundings. All right, and it's a simple equation. The delta S of the surroundings, it's going to equal the negative of delta H divided by T. So when we're looking at a chemical reaction, we have the delta H for that chemical reaction, and if we divide it by the current temperature and we take the negative of that, that will give us the delta S of the surroundings. All right, the delta H is the enthalpy change for the reaction. T is the temperature. The temperature does have to be in kelvins. A pitfall here. All right, someone is going to make this mistake. I hope it is not you. You're watching it. You're paying attention here because I'm drawing your attention to it. Delta H is typically listed in kilojoules per mole. All right, delta S is typically listed in joules per mole per Kelvin. All right, so again, delta H kilojoules, delta S regular joules. All right, so you will have to make those conversions back and forth, so just be very careful there. All right, why is there that negative sign there? The negative sign there, it's kind of to adjust. The delta H is defined from the perspective of the reaction. So for the surroundings, all right, we need the opposite of it. So if the delta H is negative, because it's an exothermic reaction, the negative times the negative would give you a positive, and that should make sense. An exothermic reaction is releasing energy. The surroundings should have that positive increase in entropy. All right. Now, since we're dividing by T, that's where we're getting that magnitude piece, right? That $50 example that I just gave you. All right. If we divide by a really small temperature, that number is going to get bigger. If we divide by a fairly large temperature, the impact from the exothermic process might not be that big of a deal. All right. Now, if it's an endothermic reaction, we know that delta H is positive for our endothermic reactions. So the delta S will be negative for the surroundings. And again, that should make sense to us. So here we're going to summarize everything. You might want to pause on this slide because it's very important. So remember, the second law of thermodynamics tells us that if delta S of the universe is positive, it's going to be a spontaneous process, right? All spontaneous processes have an increase in the entropy in the universe, right? That arrow of time. Now, we often just think about our system, but we now have a way to think about our surroundings as well. So if the entropy of the system is positive and the entropy of the surroundings is positive, delta S is always going to be positive for the universe, and it is always going to be a spontaneous process, no matter what. Now, if the delta S for the system is negative, right, which means we are decreasing entropy, and the delta S for the surroundings is negative, right? We're decreasing energy and entropy again. Delta S for the universe will be negative, and the process will not be spontaneous, all right? The reaction will actually occur in the opposite direction. Now, if we get a positive and a negative, this is the tricky scenario. If the delta S for the system is positive and for the surroundings it's negative, all right, we don't inherently know the delta S of the universe, all right? It can be a spontaneous process, all right, if the delta S of the system has a larger magnitude than the delta S of the surroundings, all right? Remember, system plus surroundings equals the universe. So if the system is more positive than the universe is negative, it will be a spontaneous process. All right? If it's the other way around, if the delta S of the surroundings is more negative than the system is positive, it will not be spontaneous. All right? Again, it'll occur in the opposite direction. And our last line, right, if the delta S of the system is negative and the surroundings is positive, we're in the same spot. We have to look at the magnitudes, all right? And we want the surroundings to have a more positive, a larger magnitude than the system, all right? So this is an important slide. We will see this in a couple of different forms, and I would be willing to bet that we'll see questions like this, certainly in any multiple choice questions, possibly in open-endeds, where we're asked to predict something like if it's spontaneous based on these parameters. All right, so the last thing I want to leave you with is a practice question. All right, so consider the combustion of propane gas. We have the balanced reaction. All right, normally we could ask a whole bunch of questions. We can give you initial amounts of both reactants. We could ask you to find a limiting reactant, do a percent yield for one of the products. Because we're making gases, we can do some different gas law type questions. All right, we are given the delta H of the reaction. It's negative 2,044 kilojoules. All right, I am just picturing that meme in my head of the guy looking through the binoculars, seeing the negative delta H and saying, that's hot. All right, so negative delta H, we know that this is an exothermic reaction. And so we are asked in A, calculate the entropy change in the surroundings associated with the reaction occurring at 25 degrees Celsius. All right, so the entropy change in the surroundings based on the heat flow. All right, we do need to convert our 25 degrees Celsius into Kelvin, so we're adding the 273, we're getting 298 K, and we just use our formula. Delta S surroundings equals negative delta H of reaction divided by T. All right, so we're going to do negative times negative 2,044 kilojoules divided by 298. Very straightforward math. All right, we're going to get positive 6.86 kilojoules per Kelvin. All right, and then it's per mole of reaction, but we're not including it there. And again, our delta S's we often show in just joules, not kilojoules. So we have that conversion there times 1,000. 6.86 times 10 to the third joules per Kelvin. So pretty straightforward equation. Again, this is only for the surroundings. Now, part B from this question, determine the sign of the entropy change for the system. Well, how would we do that for the system? What I would think about is the volume of the system. So we know it's at 25 degrees Celsius. We're assuming it's at a constant pressure. The volume of the reactants, all right, it's 1 mole of the propane gas plus 5 moles of the oxygen gas. So as reactants, we have 6 moles of gas here. Now, as the products, we make 3 moles of carbon dioxide plus 4 moles of water. So that's 7 moles of gas, right? We're going from 6 moles of gas as reactants to 7 moles of gas as products. That means we have a larger volume for the products. A larger volume means more chances for disorder, more states. So that is a positive increase in entropy. So determine the sign of the entropy change for the system. Delta S is going to be positive for the system. We already found that it was positive for the surroundings. So now for part C, determine the sign of the entropy change for the universe. We have positive system entropy change, positive entropy change for the surroundings. Positive plus a positive is going to give us a positive entropy change for the universe, will the reaction be spontaneous? Absolutely. All right. Our law of thermodynamics tells us that because we have a positive entropy change for the system and surroundings, positive for the universe, spontaneous process. All right. So that should help you have a better understanding of how temperature factors into entropy. We really need to use temperature to calculate the entropy change for the surroundings. Now that we can calculate the entropy change for the surroundings on our own, we can do the system plus the surroundings. We can figure out if the entropy change for the universe will be positive or negative. And now we can determine if things will be spontaneous or not.